Thanks very much. It's a bit like a reunion for people from University of California, Riverside, because I'm here largely because of the work that I did with Mark Hoddle just a little over 10 years ago, where I was working with the parasitoids in California, trying to stem the spread of glassy wing sharpshooter in California. So Rodrigo and I go back there. I know Julie Grangerard is in the room, I think. There you are. Hello. There'll be a little bit of a talk about what's happening in French Polynesia, and these are people that are probably much more attuned to answering some questions than what I am. But there you go. I'm also the last speaker, so I'll be as fast as what I can to get us through. And one of the things that helps with that is that science is about telling people in a way that they understand something they don't know. But we've had some really good talks already, and so a lot of the stuff that I can pull out and not talk about, you already know, because I've talked about things here today. I'll try to fall short of being a poet and explaining things that you do know about in a way that you don't understand. So hopefully we'll meet somewhere in the middle and go through that. So I'll skip over some of these things as we move through. But the glassy wing sharpshooter, we know it's native to southeastern USA and northeastern Mexico. We've already heard about the rate at which it sucks in the xylem fluid, so it's largely water, no defence mechanisms, moves into the insect at about 1 metre a minute, which is incredibly fast when you think about it. It's very, very thin, obviously, it's got a thin stylet, but that fluid moving in is incredibly fast. What moves in that fast, that's largely nutritionless, also goes out the other side. So this is footage that Mark Hoddle shot in French Polynesia, I believe, and we couldn't pay this woman enough to do what she does, and that's turn around and look up at the tree. But this is the glassy wing sharpshooters infesting a tree at a rate that's really quite high, and because they're sucking the xylem into them so fast, they're also excreting it out the other end. And that's why, if you'll excuse the vernacular, they've got the common name in French Polynesia of the pissing fly. So there is perhaps a marketing option there at a nursery in California. There was an old couple standing beneath one of these trees which had glassy wing sharpshooter all through them. A lovely fine mist falling over them, quite cooling on a hot Californian day. And then the lady turned to her husband and said, "Oh, sweetheart, these mist trees are wonderful, we should get one." We didn't have to be hard to explain that they were standing in urine. But the glassy wing sharpshooter moves through its life cycle fairly slowly. 10 to 12 days to go from egg to the 5 nymphal instars, 40 to 45 days adults. I've had adults 10 years ago when I was doing the reproductive and developmental biology lasting for over a year at certain temperatures. So they can stick around for quite a while as adults. So quite slow moving, but they're quite protected, large, conspicuous. They're a good insect to work with because they're like a big sparrow. You can pick them up and throw them around. I came back to Australia to work with mites. Sad move. The pathosystem we've heard about today already, there's hundreds of plant species. We heard from Sandy that host lists are virtually useless, and definitely agree with that, but we need to acknowledge that there are quite a few hosts already in Australia. Some of the concerns are obviously how the Xylella fastidiosa will behave when it gets here. Will we have more hosts, and will it start to evolve for other things? The glassy wing sharpshooter is not a great vector. It's, as a population, it's a great vector. It has a lot of numbers, and it does a great job when it's in numbers. The impacts it has is around the fluid loss, pathogen transmission, all the stuff that we've already heard about, cost to industry, and over here it's going to have a similar impact. Now, we've heard about grapes and all those sort of things. The one that always staggers me is the things that we possibly don't think about, and the first one up there, $52 million of damage to the freeway plantings of oleander plants in California. They're ornamental plants that were planted out on all the median strips in the freeway, or not all of them, but in a lot of the median strips in freeways in California, and $52 million is a staggering amount for something that I didn't really consider as we went through. So some of the work that we've done in this over the years is when I came back to Australia from the University of California in Riverside, Mark and I supervised a student by the name of Anna Rathi. She was a student with Plant Biosecurity CRC, and she looked at how Australian plants behaved in California, because it was a great opportunity to see how Australian natives would behave in an environment where you had both the vector and the pathogen. So she was looking at feeding, oviposition, developmental hosts of native plants in California. She was also looking at where the pathogen was in Australian natives while she was over there. And she also did similar surveys in Australia where she was collecting plants from all over Australia looking for the pathogen. So her survey of the pathogen both in Australia and in California was looking at Australian plant species, nursery plants, and in California established plants in the field, but also plantings in ag ops at University of California, Riverside, where there was a systematic planting, high pressure from the glassy wing sharpshooter, and the pathogen was in the area as well. She used PCR culturing and didn't find it on any Australian natives, either in Australia, which we know about with a big sigh of relief, and nothing in California either. Now, that doesn't mean we're in the clear, because we've already heard that it evolves, it changes, and maybe things have changed already in the last 10 years or 5 or 10 years. So what she did was, in respect to the glassy wing sharpshooter and how it may behave when it gets to Australia, is looking at feeding trials, oviposition trials, nymph trials, all those sort of things on the trees and in the plants that were in California. So the figures that I've got up there are not important. The summary graph, summary table probably is. So what she looked at was whether it was a adult feeding host in the field or in the greenhouse, a nymph development host, or an oviposition host, and whether it hosted the pathogen. So looking at those Australian natives, which ones were going to be our high-profile natives to keep an eye out for here in Australia if things did arrive. And so, with no surprises, the three in red, Hakea, Leptospermum and Swainsona, are what she determined to be the big-ticket items, because they have a yes against all those columns. So really cool work, I think, where we looked at how Australian systems might operate in Australia by going overseas and seeing how they work over there. So what about glassy wing sharpshooter? Will it arrive, or will it arrive? If it arrives, will it establish in Australia? The evidence is, yeah, it probably will, because much of coastal Australia is considered suitable for glassy wing sharpshooter. Most of coastal Australia, I mean the entire coast. So we've already seen some climax climax images up here from Rodrigo. The blue dots basically show where the glassy wing sharpshooter is determined to be able to survive with modelling. And so what it shows is that it said, yes, it can survive in Hawaii, and it did arrive in Hawaii. It can survive in the Cook Islands, and it did arrive in the Cook Islands, French Polynesia and Easter Islands. So it's making its way across the South, or not South Pacific, it's making its way across the Pacific. So the modelling said it could exist there. They did exist there, and we'll come back to that. But that means, for an Australian perspective, with these islands being so close and stepping stones onto our own shores, we've got a little bit to worry about as they come across. The modelling in Australia suggests, as I said, most of the coast around Australia is going to be suitable for glassy wing sharpshooter. Now, that's where our industry is, it's where our urban areas are, so we've got no reason to suspect that's not the case. So we probably don't have the natural enemies here. So there's less competition and fewer natural enemies than in the home range. We've got the hosts available. There's 174 known feeding hosts in Australia, 142 are also oviposition hosts, and there's no information really about Australian native plant species except for the stuff that Anna did as well. So if it gets here, will it survive? Yeah, it definitely will. How will it get here? Some of the pathways that we've got to consider in Australia and New Zealand as well is flying here, not on the wing from the insect, perhaps. You know, we've heard about how far they can fly with the little treadmill for insects, which is kind of cool and kind of punishing as well. But this is a plane that Mark Hoddle boarded in the islands, and they're attracted to the yellow tips of the wings. So there's sharpshooters everywhere, and they come here and they hang around the plane. As he was boarding the plane, he watched one fly in through the front, turn left because that's where the light was, and it got wedged between the windscreen and the dashboard. Now, I apologise if there's any pilots in the room. I'm sure we don't call that a dashboard, and it's got a fancy name. But that's one of the ways it's been moving through the Pacific. Hitching rides in planes, in the cargo holds and so forth. So there's a risk there. We had a detection of one in fuselage in Australia a few years ago. Another one for the airport is loading of luggage at the airport. Glassy wing sharpshooter was in the area. They hang around the lights at night. They load these bins at night. They hit the light, fall down into the luggage bin, get covered up with the tarps, get loaded into the bellies of planes, and then go away nice and cool, ready to arrive wherever they are. So there's a risk there with a gravid female arriving. People in the South Pacific, they're doing their best to control it moving through the islands. This is a fumigation facility to help with the spread of glassy wing sharpshooter between the islands. Now, it's not ideal, obviously, but I think it does demonstrate a real effort and an attempt to do it. This is a box. They close it up. You can see a little hole there. The plant sits inside the box, and this is basically mortine. They spray it in through the guts, and that's your fumigation. So there is real risk, not so much to Australia because we'll have different controls coming into our country, but certainly going between those stepping stones between the islands in the Pacific. And if anyone does know Mark Hoddle, that's him. You'll recognise him. It's a few years ago, but that's his cranky face because he didn't think that was much of a control technique. So what's been happening in New Zealand? 2001, they suspended imports of table grapes. It was reopened with strict conditions. We did the same thing in Australia. So everything now, I believe, is still the case, is methyl bromide fumigation. And it's all based on the danger of the vector, not the pathogen. And, you know, I'm biased because that's the work that I was doing in California, but I believe the vector is what we need to be looking for and trying to control. The biological control of glassy wing sharpshooter, there's a suite of natural enemies. We've heard a lot about that already from Rodrigo. But we probably need to be starting to consider their use in Australia and preparing for the use of biological control. So key agents have been released in California and French Polynesia. French Polynesia was an excellent example, and this is where Julie can answer questions on that, where it was almost like a replicated trial because of the way the islands were infested with glassy wing sharpshooter. Gonotrocerus ashmeadi was released on an island and not on control islands, and they watched the spread of the parasitoid as it moved around through the island. So a really clear and effective way of seeing how biocontrol works. Eventually those control islands also got infested with Gonotrocerus, and they took care of populations there as well. So in Hawaii, populations in Hawaii have been managed pretty much through the self-introduction of Gonotrocerus ashmeadi. So a lot of the risk that we have in movement is probably egg masses, which is a double-edged sword. They're protected, hard to see because they're a little bit inconspicuous unless you know what you're looking for, but they could also bring in the biological control agent along with the vector, which would be probably good. If we're going to get one, we want to get both. So mymarid egg parasitoids are relatively easy to rear, and they do multiply a lot quicker compared to glassy wing sharpshooter, so they're possible to use. So mymarids in comparison, if you remember the figures that I showed with the glassy wing sharpshooter being a lot longer, females live 12 to 16 days, lay about 30 to 70 eggs. Egg to adult is 12 to 14 days, so they're a lot quicker. They're female-based, which is good. Their biggest shortfall is having the glassy wing sharpshooter eggs for their rearing. So we can't really prepare and have a number here in Australia because it would also require having a mass rearing facility with glassy wing sharpshooter, and no one really wants that. So this mymarid parasitoid is widespread in California. In the second season, it accounts for 95% of parasitism in the second generation. So it's a bit slow to start, like a lot of biocontrols. In the spring, it accounts for less than 30, but very quickly gets up on top of the numbers, and you can see them in high numbers everywhere. So about 3 generations for every single glassy wing sharpshooter. Pretty much covered that. So the work that I was doing in California was looking at the developmental and reproductive biology of glassy wing sharpshooter and also the mymarid parasitoids. So it was horrible work, really pedestrian and boring. It was just basically putting insects in different temperatures and watching how fast they move through things. Really mind-numbing, but I watched more AFL in California than what I ever did in Australia because you could do that at the same time. But what we found was for this particular mymarid, for example, 30 degrees is about the optimum temperature for rearing, and it's got fairly tolerant low and not very tolerant high temperatures. But insects are pretty good at finding those little microclimates and surviving. As you can imagine, the glassy wing sharpshooter curve sort of stretches out either side because they're a pest, so they're really good at outside of those. So what we did was we took that data, and there was a lot more than those data that I showed there, but we took those data and produced maps. So give an indication of how successful those mymarids might be in different parts of California. So they'd really kick along down here, which is convenient because that's where the glassy wing sharpshooter, main part of the population is, and they become less effective as you move up into the cold areas. So this is the number of generations as an example of the kind of data that we can produce. This is the sort of stuff that we'd probably want to run in Australia, and it would be a simple little thing to do. It would be really plugging it into a couple of systems, using historical weather data, and then producing the same sort of map. So I think that's something we need to think about if we consider biocontrol being an option. So if I had only 2 minutes to tell you what I wanted to tell you, I'll take 5 minutes to do that. But I think we recognise that Xylella fastidiosa needs a vector. Glassy wing sharpshooter is a serious threat. Because of its ability to get here, it's big, it's tough. There is a pathway. One of those risks is the smuggling of plants, so we're always worried about smuggling of plants in Australia, and I'm sure New Zealand as well. If the egg masses arrive, then they're going to arrive ready to go, anything between 30 and I've seen as many as 80 eggs in a single egg mass, so it can be quite big. The important thing to recognise is those biocontrol agents are effective. Gonotrosis ashmeadi is halting the spread of glassy wing sharpshooter across the Pacific. It's done the job in Hawaii by itself. It's done the job in French Polynesia with a targeted release campaign, and I believe it's also doing it in the Cook Islands and Easter Island as well. It's possible to contain glassy wing sharpshooter. They've shown they can do that in California. It's not cheap, it's not easy. You alienate some parts of the industry, as I understand it, because the smaller parts of the industry in the south are virtually looking after the more expensive, lucrative industry up in Sonoma Valley and places like that. So it can be a political minefield, not cheap, takes a lot of effort, but biocontrol plays a key part in that. The area-wide management of the pest, if and when it arrives, is probably going to be our strategy as well, because when it gets here, it's going to be tricky. And that's all I really want to say. Basically just focusing on that biocontrol. I think it's time that we start thinking about pre-screening some biocontrol agents so that if it does get here, we can have an idea about host specificity, where we can use it, how we can use it, and having some of that, the legal framework around that set up so that we're a little bit quicker. Otherwise, we're going to be well behind the 8 ball when it does arrive. So thank you.